Hey AI enthusiasts! Welcome back to All About AI Tech, your one-stop shop for everything AI. Today we're going on an exciting adventure, a deep dive into deep reinforcement learning. Now, you might be thinking, DeepRL, sounds complicated. Trust me, the core concepts aren't as daunting as they initially seem. And once you grasp them, you'll be amazed by its power to solve complex problems that once seemed unsolvable by machines. Think self-driving cars navigating bustling city streets, intricate robotic arms performing complex surgeries, or AI agents mastering games at superhuman levels. It's all about DeepRL. We're talking about machines that can learn and adapt, improving their performance over time through interactions and feedback. It's a field that's not just pushing the boundaries of computer science, but also creating tangible, real-world changes in how we live and work. And if that doesn't get you excited, I don't know what will. Get ready, because we're not just scratching the surface. We're diving straight into the heart of the matter. Let's rewind the clock and cruise through the history of DeepRL, tracing its fascinating evolution. While the story of reinforcement learning goes back even further, think Arthur Samuel's Checkers program, a true powerhouse. It's the fusion with deep learning that truly unleashed its potential. The early 2000s laid the groundwork, with research showing the possibility of employing neural networks for approximate solutions. But it was the DeepMind team's success using DeepQ networks, DQN, to play Atari games in 2013 that really captured the world's attention. Remember those images? A computer agent actually learned to play countless classic video games, from Pong to Breakout, often surpassing human experts, without explicit programming. The implications of this landmark accomplishment were breathtaking. It wasn't just about beating games. It was about showing that machines could learn incredibly complex behaviors, opening doors to applications we only dreamed of before. It's impressive how quickly the technology developed. Just a few years later, DeepMind's AlphaGo caused global sensation by beating the world champion at what was seen as the ultimate, computationally complex test for AI. The key here was building a system that combined the best of tree search with DeepRL to dominate. Then, AlphaZero, an even more powerful system, further established the potential of DeepRL, demonstrating superhuman performance in chess and shogi on top of Go from scratch within 24 hours. This clearly demonstrated DeepRL's ability to tackle complex tasks effectively and efficiently, further fueling this revolutionary field's expansion. Now let's dive into the heart of DeepRL, the algorithms. We'll start with the foundational one, DeepQ networks, DQN. This was one of the first models able to achieve superhuman performance in many Atari games. DQN is built on the concept of Q-learning, a type of reinforcement learning. The innovation here? DQN leverages a deep neural network, instead of tables, to estimate the expected reward for taking any action from any given state. Let's try to visualize this. Imagine a chessboard, each position a state, and each potential move an action. DQN learns to find the optimal action, that is, the move that maximizes the agent's expected future reward that can be obtained by reaching a certain state, such as a checkmate, based on its learning experience. The network's parameters or weights encode its learned skills and are continuously adjusted based on the observed rewards. The brilliance of DQN lies in its ability to learn complex actions and strategies directly from high-dimensional sensory input, such as images of the game screen. There is, however, a trade-off between the reward exploration and exploitation, meaning that to learn a winning strategy, the agent needs to sufficiently explore its ability. One way of solving this exploration-exploitation trade-off is based on the addition of exploration noise in the selection of actions. The original DQN algorithm, however, suffered from instability. To fix this instability, DeepMind implemented two clever tricks, experience replay and target networks, which play a massive role in scaling training. Imagine the agent storing previous games' trajectories in a kind of memory bank. DQN draws a small batch of these trajectories from this memory bank to avoid the correlation between updates, resulting in more stable training. Furthermore, the target network, or critic, learns from a slower update of the main learning network. By separating action selection from value evaluation, DQN achieves stability, setting the stage for more advanced methods. Next up is Deep Deterministic Policy Gradient, DDPG. Unlike DQN, which deals mainly with discrete actions, like choosing one of the chess moves available for any position on the board, DDPG handles continuous action spaces. Imagine those same pieces on that board, but instead of selected moves, we control their velocity and direction. The same game, but with a whole smoother, infinite space of actions available to the agent. This is the realm of continuous control, which has crucial importance in areas such as robotics where controlling movements with continuous values is required. This is precisely where DDPG shines. DDPG utilizes an actor-critic architecture, splitting the network's efforts into two parts: the actor network or policy network that determines how an agent should behave based on its observed state, and the critic network that estimates how good any action might be. This critic plays a critical role in reducing variance during training. Using an actor-critic framework is similar to having a coach guiding and reviewing a player's game moves while playing. The actor decides an agent's moves, and if this works, the coach gives a positive review which causes small adjustments to how the actor learns to play. Both the actor and critic are implemented as deep neural networks, capable of processing high-dimensional inputs and improving their performance over time. But DDPG also inherits some problems from DQN: poor exploration and instability. To fix these problems, and inspired by DQN, DDPG implements exploration noises via the Ornstein-Uhlenbeck process and employs target networks and batch normalization for more robust performance. Let's move on to proximal policy optimization, PPO, another superstar. PPO tackles policy gradient methods more effectively than earlier methods like reinforce and TRPO by avoiding large changes in the model's predictions. This ensures stability with each update while enabling quick improvements. Imagine balancing on a tightrope. Small adjustments keep you stable, while large ones usually cause a fall. PPO takes a similar cautious approach, updating the decision-making policy, i.e., a neural network that outputs the probability of taking any given action gradually to maximize reward, ensuring that the policy changes incrementally, avoiding drastic jumps in performance. PPO solves these issues by using two methods or tricks: clipping and generalized advantage estimation. Intuitively, the clipping method is designed to prevent large changes, ensuring that the policy stays within a reasonable neighborhood and avoids sudden performance drops. Generalized advantage estimation, GA, improves the reliability of reward estimations by considering a range of future reward signals on top of immediate ones. Think of estimating an athlete's performance. A single race might not give a good indication, but averaging many competitions gives a far better perspective. PPO is praised for its strong performance and ease of implementation, making it a popular choice for both research and real-world applications. Its robustness shines in various conditions and environments, making it an exceptionally versatile algorithm. Let's briefly discuss two more prominent DeepRL algorithms: Trust Region Policy Optimization, TRPO, and Soft Actor Critic, SAC. TRPO, another policy gradient method, aims to improve stability by constraining how much the policy can change to ensure smooth development and maintain a reliable strategy. Think of it like slowly adjusting the settings on a complex machine. Tiny tweaks prevent sudden breakdowns, even if it takes longer to find the ideal arrangement. Its emphasis on gradual refinements makes it particularly adept at handling difficult control tasks where stability is paramount. However, this method comes at the cost of complexity in implementation and slow convergence, making it less widely used comparatively. Soft Actor Critic, SAC, distinguishes itself as an off-policy actor-critic algorithm. This means that data gathered from the policies it has previously explored can be used to update the current policy, which in contrast to on-policy methods, uses only data from the current policy. In this way, data is used more efficiently and can often reduce the training time required significantly. In addition, SAC seeks to optimize the policy and the amount of randomness in the selection of actions, balancing exploration and exploitation. The increase in the maximum entropy policy results reduces the risk of the algorithm converging to a suboptimal solution. Now for the exciting part: DeepRL's applications. The examples are endless, spanning diverse sectors and revolutionizing how we approach complex problems. Let's start with robotics. DeepRL empowers robots to learn dexterous skills, like handling delicate objects or navigating complicated environments. This is done without human intervention, opening a world of possibilities for industrial automation, surgery, manufacturing, and exploration. Self-driving cars represent another massive application domain where DeepRL is enabling safer and more efficient autonomous navigation in highly dynamic and complex environments like city streets and highways. In healthcare, DeepRL algorithms are utilized in drug discoveries and personalized medicine, optimizing treatments and enhancing patient care. In gaming, we've actually seen DeepRL reach superhuman levels. We've witnessed DeepRL's incredible capacity to conquer complex games, from Go to StarCraft. This achievement showcases its potential to improve strategy development and optimization across a range of applications. In finance, DeepRL helps manage investment portfolios, make predictive decisions, and reduce risks in dynamic markets. DeepRL has also been applied to energy management systems, improving grid stability and resource allocation, and even in optimizing the operations and planning of supply chains. This versatility is truly remarkable. This range of application is extremely widely spread across the industry already, and its practical use cases are continuously growing. Despite DeepRL's clear successes, certain challenges still hinder its pervasive adoption. Sample efficiency stands out as a significant concern. Training DeepRL agents can require massive amounts of data and computational resources. While this might be acceptable in research, it can constitute a bottleneck in the real world and in many applications. Stability remains an issue. The training process can be unpredictable, even resulting in agents moving in directions that would seemingly conflict with optimality. Generalization is another big challenge. Agents can often perform well on tasks they've trained on, but not too well on other types of tasks that are either conceptually similar or even completely distinct, even if such tasks seem closely related conceptually or intuitively. Designing reward functions that can truly capture the desired behavior also presents a considerable difficulty and requires significant design efforts. The reward functions, in essence, are the mechanism employed for communication and feedback in between the policy function and its environment. For various reasons like being time-consuming or even simply being human error-sensitive, the manual tuning of reward functions could constitute a bottleneck for scaling up DeepRL to wide-scale applications. In the future, we believe research focusing on developing more sample-efficient algorithms, enhancing model generalization capabilities, improving training stability, and streamlining reward function designs will be invaluable for wide-scale adoption. This ongoing research will allow for the development of additional and increasingly more intricate and potentially more effective DeepRL techniques. The ability to combine DeepRL with other AI techniques like natural language processing, NLP, and computer vision, CV, represents another area of critical interest. For example, this combination opens avenues for training robots with both visual and verbal directives, developing an even more advanced and adaptable system with capabilities that are significantly beyond that of what is possible today. Furthermore, DeepRL is at its early stages. The rapid rate of progress of its recent years is likely to continue. It's a field with vast, uncharted territory, with an enormous potential to shape the future of how we build intelligent systems. In turn, this will result in continued improvements and exciting new approaches toward tackling complex problems.